All right, so this is the ArcGIS Pro Workshop, and it is Thursday, October 1st, just after 3 p.m. Eastern Time. And this one's going to be a little bit different in that usually what we'll do with these workshops is we'll go down and we'll explore some of the technology. But I have a sufficient number of clients that are constantly asking me about curves and how they work and trying to explain to them that I realize that there really needs to be a little bit more education about curves as a whole. I can share with you that as a surveyor, these are one of the things that they really focus on. How do you build a curve? What is it and such? So overall, that's all we're going to do this time. It's just going to talk about curves, and as you can tell from my title, curves, and then more curves, and then more curves. It's just going to be curves, curves, curves. That's all it's going to be. And then at the end, if we have any time, I'm not sure we're going to, but if we have any time, we'll go ahead and have some discussion about other components of it. But we're going to talk about simple curves, about the components of the simple curves, angular relationships between them. We're going to just on a very high level just talk about some of the trig functions, trigonometric functions, and the relationships between all these components. And we'll talk about tangent curves and non-tangent curves and compound curves, reverse curves, points of cusp on curves. And then we'll show about creating them through in ArcGIS Pro through using constraints, construction constraints, and then we'll see about maybe creating them in a traverse and see what elements you can put in there, what it actually stores, and then how to go and create some with fillets once you understand all the components of it. And then if we've got time, maybe spiral curves, and then maybe a discussion about, well, of all these components that we're putting in, which ones are the most accurate and which ones should I use? That sort of thing, and then just open it from there. So that's sort of the general layout for what we want to do today. Like I said, it's going to be a little bit different. There won't be a whole lot of ArcGIS Pro in here, but more of a primer on curves. What are they? How do you work with them? So let's just start by actually creating a curve. All right, I'll go in here and I'll do this, and I'll do it as simple as possible. I'll use the circular curve component, and I will put in a tangent curve or a tangent direction. I'll put in a radius, and this time I'll put a direction or a central angle of 45 degrees. So let's just explore what that means, what that is. All right, and then let's explore the various components of it. Let us go and label here, and let's put our labeling on and label this. So there's the arc length of the curve. All right, that's actually the arc of the curve, and the curve is actually defined as an infinite number of points, a single distance from a radius point. So let's look at this. I'm going to go in here and let's create some of these components on it. So if I go here, and in this case, I know that when I created this, thank you, Tori. When I created this, I actually created a curve that was a set distance away from a point. That curve was actually, that curve was set as 100 or 250 feet away from a point. That point is called the radius point. And if I go from that radius point up to here, this is again the radial line for that curve. All right. Now the curve itself is defined as starting on one point. In this case, this is the point of curvature over here, and ending on the other point. These are called the point of curvature and the point of termination of the curve. And then these are defined as the radial lines. This point down here is called the radius point. All right. So there's other elements in here. So for example, if I have a line that is perpendicular to my radial line, all right, and let's start this again and see if we have a point over here that is perpendicular to this radial line. Let's go and take both of these, and these are called tangent lines. All right. Let's also go and go in here and planarize these or intersect these and get rid of these other elements on here. So the point where these tangent lines intersect is called the point of intersection. All right. It's the point of intersection. All right. And that's the intersection between the two tangent lines on here. So let's go back here again and create some other components on here. If I create a line from the point of curvature all the way to the point of termination, this is called a chord. All right, so with that right there, we have the simple components of a curve. We have the arc length, which is a critical part, the radius, the radial lines, and by definition, the length of those radial lines is called the radius. That's the radius distance. That's how far away from this radius point these arcs are actually being created. And it's a series of, again, by definition, we think of them as a series of points, not necessarily a line, but within GIS, we represent them as lines. And we think of them as a series of points because any point on this arc length is actually a full component of a curve. And you can actually figure out how to calculate how to get to that point, how to go and locate that on the curve. There's a whole bunch of elements in here. All right, so again, 90 degrees to this radial line is called a tangent line, and that's off of each of those radial lines. Those radial lines where they intersect is called the point of intersection of the tangents. All right, those are all important terms when you're dealing with this. So there's some interesting things in here, in that if we look at this, and let me put one more line in here before I do this. I'll go back here. All right, let me put one more line in here. I'm going to draw a line from the radius point to the point of intersection. All right. And when I look at this now, I can actually see that if this is 90 degrees, if the tangent line and the radial line are at 90 degrees, then the total angle included within a triangle is 180 degrees. So that this angle here and this angle here have to total, these two angles plus this angle have to 180 degrees, or these two have to add up to 90. All right, but an interesting thing, and by the way, this is now, these two are equal because the tangent distances are both equal. This angle that is subtended, the angle that's created by the two radial lines, that's called the central angle or the delta angle. The delta is the change, that's the change angle, or the central angle on here. Well, we get some interesting things here with geometry because this is really nothing more than a series of right triangles, 90-degree triangles, which means that in fact, this angle here, let me go back here to drawing again. Let me get out of here. Go back to I'm trying to get my drawings back again. All right, so that this angle here, again, this angle here is the same, or let me put it this way, it's 90 degrees minus this angle here. This angle here is the same as this angle here. All right. So my central angle here is the same as the angle between this tangent line and this tangent line. These two are the same. All right. Because of the way the geometry works within this. Brian, thank you for showing me that. I wanted to draw it out myself just to make sure I knew how to do it and remembered how to do it. But they're exactly the same. But interesting things happen now. Is that, okay, well, remember that line we drew here, which connected the radius point and the point of intersection, and then the chord? When we drew that chord, well, it's actually, this is 90 degrees here. All right, which means that this angle here is 90 degrees minus this one. And clear this out because this sort of gets some redundancy in here. We get down further and further and further. It means that this angle, I'm sorry, means that the drawing tool doesn't want to stick. All right, that this angle is the same as this angle. All right. So it turns out that the curve itself and the components that make up the curve, the radial lines, the chords, the tangent lines, this long line here, this is nothing more than a series of right triangles on here. And if you know two of the distances, you can figure out the third distance. You can figure out the angles on here. And that's how, when in GIS, they give you, okay, well, give us the radius distance. All right, you got that. And then give us the arc length or the chord length, or give us the arc length. These all have trigonometric relationships between one another. And those relationships are defined by these components and these relationships within triangles. All right, let me erase this again. Get back here. Back to here. So again, if we understand that the curve itself is nothing more than a bunch of triangles in here. By the way, that relationships, this is a tangent distance, this is a radial distance. This, if we were using sort of the Pythagorean theorem, the old Greek theorem, right triangles, that side A, and let's call this the tangent side. Let's call this the radial side. Let's call this the hypotenuse. That the square of this is equal to this side squared plus this side squared. All right. The hypotenuse squared is equal to the opposite squared plus the adjacent squared. These are simple, first level trig functions that are in here. But that's how a curve is actually formed. It's just connecting up with an infinite number of points that are the same distance away from a radius point on here. Any comments, any questions? What did I make real fuzzy here? What did I not make fuzzy? Any questions or anything? By the way, if you have any questions or anything, you can chime up or you can ask Chris. Chris is actually moderating this today, so you can ask him.
We don't have any questions in the chat right now.
Okay. So I could go deeper. I'm not going to go deeper, but I could go deeper if you wanted to. Right now, what you see on the screen is the basic components of a curve. And what we're going to do is we're going to talk about how you can build on those components and make them into additional more and more complex curves. This is usually how a simple curve is defined, is just those elements in here. All right, there are radial lines, there's a chord distance, tangent distance, arc length, and the central angle on here. This is the central angle from here to here. The radius distance is from here to here. The chord distance is from here to here. And the arc length goes here. The tangent length goes from here to the point of intersection. All right. Now, once you understand those, then we start making it a little bit more interesting. So let's go and say, well, if that's the case, what happens if we want to have one curve which is built on the curve of another curve? All right. So let's go in here and go to create, and we'll do a new curve here, and we'll start here. But this curve is going to have a shorter radius. So what we can do is we can go in here to a curve and say that in this case, we're going to take a tangent distance off the previous curve, and our radius now is only going to be 100 feet. And there it is there. So again, I can now build the same components off of this. I can go and say, well, if I go in here, and I go down a distance of 100 feet, that's where my radius is for this curve. And there is my other radial line for this curve. This is the chord distance for my curve. And if I go parallel to this, there's the tangent for this curve. If I go perpendicular to here, there's the tangent to this curve. If I go and go in here to extend trim, where are we here? All right. Extend trim. I now have all the various components. My radius point, let's get off of this. My radius point, point of curvature, point of termination, the point of intersection, my tangent line on here, the angle between this, the chord distance, and the tangent. By the way, that is not. This is actually, that arc length is on there. This is the chord on here. There we go. So the angle, again, between here, the tangent, and the chord is actually equal to 1/2 of the overall central angle here. So when we're asking to go and figure out how something relates to something else, there's a couple elements we need to understand. And this is again, you need this every time you go and put in a curve. You need to understand what the radius distance is, always. That is probably the primary component of it. For those of you that were in the meetup yesterday for parcels for land records, there was a discussion about someone had put up on the idea site. Maybe there's a way for us to be able to go and input something other than the radius. Maybe put up the chord distance and the tangent distance, or the chord distance and the arc length. Can you develop a component of that? And Esri's response was, it's not a bad idea, even though that means that you're using something that's not as important as the radius for determining the actual other parameters of a curve. Because once you understand the relationships here, you really only need 2 components to build a curve, right? Because these are all related to one another in the tangent, or excuse me, in the right triangle. You can understand and build everything else off of them. But you have to understand at least 2 components to build everything else on here. Which 2? The reality is it's any 2 of them. You can build everything else. You can have the central angle, you can have the tangent length, any 2 of them, you'll be able to go and figure it out because of these interrelationships that are defined by these right triangles. Not as easy, because you start using things like arc tangents and arc sines when you go in and use this, some of the more advanced trig functions to calculate things, but you can do it. And so in fact, someone was asking Esri, can you build that in so that we don't have to go back and always put the radius in? So those are 2 of the components that always have to be put in here, but there's another one that's more important. And that is, what is the orientation of this curve? How does it orient to the line that I just built? Because I'm going to go in here and I'm going to select this curve and this component on here. And I'm going to go and actually rotate it around my point of curvature. In this case, let me go and do something else first. Let me turn off my topology. All right. So in this case, this curve is oriented so the previous line, the end of the curve before it, and the next tangent are not the same. Again, this tangent line and this tangent line are not the same. So this is not a tangent curve. This is not built off of tangency between the lines themselves. Previously, when I built it the first time, because they had the same tangent line, this was a tangent compound curve. Two curves having the same tangency line, but having different radiuses on them. So when you are inputting a line, one of the first things that they will ask you, and if I go and create another curve here, input this and go to curve, what's the first thing they ask me? What's the orientation of this curve? What is the tangent direction? What's the chord direction? Or what's the radial direction to this curve? So what is the bearing on that line? What's the bearing on this line? Or what's the bearing on this line? It needs to know how and where to locate that radius point, most importantly, but how does this relate to where you're sitting right now? What is the tangent on here that I can use? What is the chord bearing, or what is the radial bearing? How do I go and build those so that I know where to put, importantly, where to put that radius point? Because that from there, everything else is going to get built. That's why, again, within the traverse and within any time else when you're building a curve, you have to give it two of the curve parameters, and you have to give it an orientation. You have to give it some sort of bearing, either for the tangency, for the chord bearing, or for the radial bearing. You have to give them three components. It has to be one direction component, one orientation component, and two curve components on there. All right, so in this case, let's just say tangency is let's do 90 here. All right, and 100 center angle. Let's put a chord distance in here. Let's make this 100 feet. And then the only other question is the curve going to the left side or to the right side? What does that really mean? That means that when I'm developing this, all right, when I'm developing this and my line and defining where the radius goes, is the radius point over here or is the point over here? Right? Because this could get flipped completely. It could have the same tangent bearing and it could be flipped back and forth. So they need to know this to figure out, well, where do I put the radius point? Do I put it on the right side or do I put it on my left side? And that really is what that means, is which side of this bearing that you're going to be telling me, which side of the line where I'm going to be going forward, do I put the radius point in here? And let's just go ahead and build this. All right. And we can go from there. So we now understand all these components on here. When I describe this to somebody, usually what I'm saying is that if I build a line, and let's just build a line here. All right, say okay from there. I know you failed to do that. See, he's going crazy right now. Sorry about that. I think it's because I'm flipping back and forth between all these different pointers in here. It is not liking this. All right.
Looks pretty cool from here,
I know it. It's flashing, isn't it?
Yeah.
It is flashing. So let's go and select this here. Now let's delete that. All right. Let's go in here and create. And we're going to create a curve component. And just create that. So when I'm creating a curve now, I need to know what is one of these bearings? What's the orientation of my curve? Is it going to curve over to this side? Is it going to curve to this side? And usually when I'm describing it to someone, I will say, well, picture that this is a road and you're traveling down the road, all right? And you have to figure out, are you going to turn your steering wheel to the left side, or are you going to turn your steering wheel to the right side? Now, since we're all here, we understand a little bit of geometry, we don't have to use that analogy, but it's sort of meaningful, all right? Which way are you going to make that curve go? Is it going to go to the right side or left side? And that's why you have to go and understand that sort of where is that radius point going to go. All right. Once you've got that in place, then we can go ahead and let's just build a curve here from here. And all right, start here, and I can say circular curve. And in this case, because I went back over on top of my other line that I had, it picked that up inside of my constraint and said, oh, if that's your tangent direction, then I could go and put the rest of this stuff in. And again, then it's okay, well, what's the radius? And what's the central angle here? Maybe I want to go 60 degrees east from there and go from there. Now, once I put that in, it already has that in here. And if I go to create another curve from here, it will understand what that is. I can go to the left. Now on here, with this type of curve here, in this case, it turns out, there's my chord. I'm sorry. No, I didn't make that 60. What did I make that? Anyway, so what happens is, because of this, it turns out that through here, that these two curves, all right, these curves previously, these were called compound curves. This curve is called a reverse curve. Actually, this is called a reverse compound curve. It is one curve connected to another curve. But in this case, the radiuses are reversing whether or not to the right or the left. Compound curve, reverse compound curve. All right. Any questions yet? None. None. This is again, if you've ever been to a trig course or geometry course, this is simple stuff here. But again, if you've never been in a course like that or never taken any of the Florida Association of Cadastral Mappers courses, you need to understand this geometry and how it works.
Frank,
Yes, sir.
this is Brian. Can I interject? Will you show us how to enter these curves in the traverse?
We will. That's one of the
Okay.
things that's coming up. Yeah, we are going to go and do that.
Great, thanks.
Yeah, good. Thank you. Good suggestion on there. All right, so we have one other type of curve I'd like to show you. All right, and I'm going to go and take this and this. What happens if we have a curve in which I go and put a curve in here? All right, and this curve, let me go and select this instead. All right, this is the distance here. And this curve goes, and I'm going to create all right. This curve does this. All right. And you may not find it very often, but there are instances when this is what these curves look like. All right. In which they are non-tangential, but rather than being, they're sort of like an exaggerated non-tangent reverse curve in which you start at this point, here's the point of termination, and it goes into another curve here. This point right here, this point at the end of that, this is called a point of cusp, C-U-S-P. This is very problematic both for the way it gets input into ArcGIS, in that some of the ArcGIS algorithms to create these things really don't understand all of it. But often people get confused, well, how do I put this in? You put this in so that things such as, again, here's my curves or my chords between them. You put this in so that this curve is defined by where does the radius stand relative to the curve itself. The radius is here, so this is a curve to the right. This is also a curve to the right, but you define the orientation on it differently. All right. One more thing, and then we'll start talking about inputting these in a traverse. So let's go in and input a simple component. Let's say we have a street center line in here. All right, and we want to go and build a cul-de-sac. Now we actually have a new cul-de-sac tool on 2.6, which allows us to take a selected line as the center line and then tells us, all right, where's the street width? In this case, let's make it 50 feet wide. What is the radius of this main curve here? And let's make this a 60-foot wide radius. And then what's the radius of these smaller elements in here? And let's make them 25 feet. All right. So what I want to show you is that inside of this, Actually, I don't even have to go there. I can go here. That what I really wanted to show you is the fact that the cul-de-sac itself is, again, nothing more than a series of right triangles on here, in which this is that large radius distance that was input. All right. This is the small radius distance that was input. This is the small radius for the curve. This is the street width, small radius, large radius. It really isn't that complicated what gets built on here. This is a right triangle here. This is 90 degrees. This is a right triangle here also. All right, so this is not, it's not rocket science. This is simple little geometry to go and build these elements in here. All right. Let me get off of here. Erase this out. Go back to here. All right. So up until this point, you've been seeing me and watching me going and inputting all of this using the create tool and using just simple line features, clicking on a line, right clicking and going to circular curve, circular arc. I actually like the way Esri has put in this tool. It actually works very nice. You can tell it, again, what is your direction? How is it going in here? What's your tangent direction? Let's go tangent to due north. All right. Here's an interesting thing. You cannot hit enter here. You have to hit tab. That's another one of the suggestions. Let's see if we can fix that. So there is my tangent distance. So this is going to go due north. My radius is going to be 100 feet. And then either my central angle, my chord distance, my arc length, or my delta angle, my central angle on here. I can put any of those in here. And then my direction, and hit enter, and it puts it in. That's a really useful tool. And by the way, you can use that in conjunction with the traverse tool on here. So I always go and tell someone, if you're not quite sure how to input it inside the traverse, cheat a little bit and input it using the circular tool, the circular curve tool. And when you hit return, it gets entered into the traverse tool. So it lets you preview what you're going to do on here before you get to that component on there. All right, just a simple little tip on there. So now let's go to the traverse tool and let's see if we can figure out how to go and input this. Let's just input a line. Let's say it's 90 degrees due east, and we're going to use 150 feet on here. So there's the feet. Now again, the difference between the ArcMap traverse and the ArcGIS Pro traverse is as soon as I hit enter there, I now actually have a line there. All right, so it already has a line and it records in its memory, okay, what is the bearing and distance of that line? So it already knows what my tangent bearing is if I want to go and use that. But if I'm going to put a curve in here, let me go and expand this a little bit for you so you can see this. If I'm going to put a curve in here, and here's where it is very different than ArcMap. At the moment, there is no default setting for this. It doesn't know what this thing is going to be. So I have to tell it using one of the shortcuts what this bearing is going to be for me. In this case, I can say that this is a tangent bearing, a TB. All right, that will then tell it that this is a curve. This is not going to be a straight line. And this is muy importante. This is más importante de los todos. This is the most important thing. If you forget to do this, you're going to go back and redo this whole line. You have to do it right the first time. I can then hit enter. I can hit enter here. And then I'm going to tell it my distance. I don't want to create a distance. I want to instead put a radius in here. The radius, again, if it's a positive radius, it assumes that the radius is to the right. If it's a negative radius, it's a radius to the left. So let's make this a 250-foot radius. And then the next thing is, well, how do we put in one of those other parameters? And remember, the parameters are the chord distance, the arc length, or the central angle. Well, it turns out that we actually have them in a pull down here. But we're going to experiment with this. So let's go and say that this is a delta angle here. All right, so this is 90 degrees. Enter. Worked perfectly. By the way, it then gives me, this is the tangent bearing coming out of that curve. So I already know what the tangent bearing is for this. All right. So I can put in here, tangent bearing. It remembers 0 there. I can tell it that this is a negative 200. And now the question is, am I going to input the bearing, or excuse me, am I going to input the central angle out here, the delta angle, or am I going to input something else? And this is where I've had some different results coming out of here. So if I input that maybe this is a 75-foot chord distance, see here? That used to be in ArcMap, the override on this. All right. Did that come out right? Let's see what the attributes on here. In here, it recorded an arc length for a curve, but it did not record the actual radius or the distance. Let me go and expose on here. The shape length, so we can go and I actually have to save some of this elements here. And let's save this so that now I can do a select and do the attributes, and I thought I just exposed that. Shape length. Shape length, 75.446. That doesn't sound right, does it? That sounds like that's actually the arc length on here. In ArcMap, in the ArcMap parcel fabric, the shape length field used to be the chord distance. And we used to have a trick where it would record the distance field as being the distance from the beginning of the curve to the end of the curve, or the chord distance. And you could actually go back and manipulate it and change the radius, and it would change the radius on here. Within ArcGIS, that is not the way this works. All right, That is not the way it works. Let's go back here to the traverse again. Let's start. Let's go and have a by the way, this is now my chord bearing. Let's reverse this around. This is 0. My radius is now 150 feet. I said that's 0. Frustrating part about the traverse. I can't capture that on here. Sometimes you can go and just overwrite it, but it still remembers that that was digitized and it wants it to be that. So what I'm trying to do is just create something here. And let me just go and say, this is 15 feet southeast. This is 0. New. 15 feet southeast. 0. Radius of 150 feet. In this case, I'm going to go and give it an arc length. An arc length of 75 feet on here. Why is this? Why is that? It shouldn't be that. It should be feet on here. It recorded as feet, even though it said it was going to be DMS on there. All right, if I look, and actually select this one instead, it is 75 feet is the arc length, 75 feet is the arc length here, and the radius is there. So what happens? What happens as far as what it stores when I go back here and I say, all right, let's go and do let's use this as my tangent curve again, my tangent bearing, and this is now 150 feet, but this time I want to record the chord length on here, 75 feet. .75 feet is a chord length, and it recorded 75 feet is my arc length on here. So I think there's still work that has to be done on the traverse to let you flip back and forth like we used to be able to flip on curves.
So Frank,
Yes,
this
sir.
is Brian. Can I interject? So usually if I'm doing a legal description or something like that, I usually get the chord distance, the chord bearing, and the radius. So what would be best practice to, if I can enter those things? What if I don't have any of this other information?
Good question. So let's finish with this. So, and good question there. So on here, I want to warn you that the current traverse, the current iteration of the traverse expects that you will be using the same thing every single time in that traverse. and it wants you to have and input the same thing every single time. So if you've got a legal description that uses the same curve references, set them in the beginning and then just use the same thing every single time. Don't flip between the settings that you use for different courses. All right, don't do that. It doesn't work yet that way. It's expecting the same thing every single time. And sorry, Brian, I'm going to finish one more time here. So with this, let's go in and make this a tangent bearing, 0, make it 150 feet. And this time, let's put a central angle in here with an override. Remember the old overrides we used to do? So let's say this is 90 degrees, and that old override used to be D, correct? All right. So in here, select this and see what it actually was recording as. This may have used that override on there. Let's try, now that we know what we can do with this. So those are good questions, Brian. I've not forgotten you. By the way, one of the things that bothers me, and you've seen it here, when I'm doing 2-point curves, it keeps wanting to extend it here. I can actually, on 2-point curve, I can go over to this arrow, and on here, there is, with this, whether or not you want to continue 2-point curves afterwards or not. All right. So now when I go here, I can do this to this. I create that. Let me see if I can go into a new, share a new element in here. Measure distance, measure offset. Can't do that. Modify here. I think we have intersects. Line intersections. No, that's not it. Sorry, I thought we could do a distance intersection and get what this is in here. All right, I'm going to give that up. Went down a rabbit hole there, wasn't worth it. Going back to your question again, Brian. All right, so can you remind me again, Brian? You were asking me what is the best, or what is the best way to do this, right?
What would be best practice? Like I said, usually I get a chord distance, I get the chord bearing, and I get the radius. Usually nothing else. So if I'm just, I got a, long legal description with a bunch of curves in it, what's the best practice that it doesn't take me the entire day to put this one description in?
Actually, that's one of my questions towards the end here. What's the best practice on this? So here's what I can tell you. The most accurate components of the curve are the radius distance, and I'm going to put a big caveat here, the central angle. All right. And that's for most curves that you encounter on a normal type of subdivision. So if you want to be the most accurate, have your settings so that you're inputting the radius distance, and then you're inputting the delta angle or the central angle. And the reason for this is that both the chord distance and the arc length are rounded to the closest 1/100th of a foot. So that if you're calculating things and inputting things, it's more accurate to go out to that angular measurement and let it round the other components off, because that angular measurement is only rounded to the closest the closest whole second of a degree. All right, a degree, 360 degrees in a circle. Every degree is split into 60 minutes. Every minute is split into 60 seconds, so that a degree is much smaller than a tenth of a foot or a hundredth of a foot on most curves. Now, I say that that's the most accurate thing for most subdivisions, because most subdivisions have fairly small radiuses on them, small being less than 1,000 feet. All right, but there is a special instance there. If it turns out that you have radiuses greater than 10,000, greater than 1,000 feet, and I'll say 1,000 feet is probably a good cutoff on there. What happens is, because of rounding on the angular measurement, in those instances where you have a very long radius, the actual distances that are measured are more accurate than the center angle. So Victoria just put something in the chat window I saw. Surveyors tell her they want her to use the chord and chord bearing to enter curves. And the reason why they do that is those are the bearings that they go and input into the plats. That's what they get recorded out of in their CAD systems and such. But the reality is that the chord distances are rounded. All right? They are rounded to the closest hundredth of a foot. All right, so to answer your question, Brian, if it turns out that, let me go parallel here, and I'll just draw this for Haraz, all right, that for very short radiuses, all right, for a radius from here to here, for example, this angle will be more accurate than the measurement here. But when you get into curves that have very long radiuses, the rounding that occurs on this can mean a great deal of distance here. All right, 1 second in a 10,000 foot radius curve might be a foot. All right, so just recognize that in most instances, when you are inputting the traverse information, the curve information for a subdivision, you would use the radius, distance, and the delta angle or the central angle for creating your curves. When you're doing that, it's a really good test, because as you are inputting those, go back here, as you're inputting these, and let's go and create a new one here. Let's start off here. All right, as you're going and doing a curve, let's go and now make this the tangent bearing. This is 0. Our radius is now 50 feet, and our central angle is 45 degrees on here. As you're doing that, it will then go and automatically calculate the tangent bearing out of that curve. All right, so as you're inputting this, as you're going along the right of way, you can use that as a double check for that surveyor, so that you can check to see when you're coming out of a curve and going into the next straight segment, do your bearings match? And it should come down to within, a second or two on there. Depends on the plat and where those are, but it should come down very close. It will serve as a check to make sure that you have input that curve correctly, that it was the assumption you made that this was a tangent curve, all works out correctly. So my recommendation is when you're doing curves inside of a subdivision and you are building the right-of-way line, use the radius distance and use the delta angle or central angle, no matter how they referenced it. Use those two. Don't use chord distance because that is rounded. And what you will find is that if you've got a series of these, where you've got a whole bunch of curves, there is rounding error accumulating. It might be 5 thousandths this way, 5 thousandths that way. But once you're running through 10 or 15 of them, that means that at the end, you might be 400ths off, or your bearings might be off because those rounding caused those bearings and those tangent bearings to be off. So if you're dealing with curves in a subdivision, I would always use the radius and the central angle or the delta angle. It's a really good question. That's something. But remember the special exception, which is a long radius curve. Then you can use the chord length or the arc length on there, because in that instance, those are more accurate than the central angle. Central angle has a rounding error in there, which causes a greater difference. Thank you, Brian. Good questions. The only other thing I have here is a discussion maybe on going and utilizing, for example, the fillet tool. All right, so with the fillet tool is fairly new, and it allows you to go and input and connect on what we now know are tangent lines. So if this is a tangent line coming in, and this is a tangent line coming out, this would then be the point of intersection of that curve. So that now I can use the fillet to say, go here to here, and there is how my curve would fit if that intersection of those two lines is the point of intersection, and I can click here and it would trim them up. And I guess
Frank, Eric has a question in the chat.
Yes.
He says, if your legal description gives you chord and chord bearing, but not delta angle / central angle, would you calculate the delta angle / central angle from the chord and chord bearing?
No, unfortunately. If all they give you are the chord and chord bearing, and this is recorded, so I'm going to say it, they are lazy surveyors, right? They're lazy surveyors. If all they give you is a chord or chord bearing, don't go and calculate the central angle, because it's already going to be rounded then. Just use what you're given, use the chord and chord bearing in there to go and actually input the curve on it. All right.
And Mark has a question as well. He says, in ArcMap, we could enter traverse using a series of from and to point numbers, which was nice for setting up a subdivision or allowing some lines, curves, to be more accurate than others. Can we do that in the Arc Pro traverse tool?
Interesting, Mark. So on the traverse tool, it would help if I could spell on the traverse tool. So Mark, you were saying that you could go and input another 2 point, right? Another point here. and connect that? That is, by the way, a good question. And the answer is, I don't think so. You can input here. You can input a dx, dy, or an absolute xy for the end of the curve, but that's not going to give you the other parameters of a curve, right? The ArcMap construction tool. So in this tool, the constraint on there, or what's the old curve construction?
And Frank, maybe I should correct myself. So in the construction, our new construction in the ArcMap fabric, we were given a series of entering in from point, bearing distance, radius, and that would go to a point. And, you know, we could just add line by line and by line, and we might not even notice it, but we'd have a number 1 and number 2 by all the vertices. And that allowed me to go back and make more complicated sublots. And also when I'm adding curves and whatnot, sometimes you don't necessarily know all the parameters that you really need. Sometimes the real only information that we might have is a radius. So it'd be nice to kind of go from the starting side and then from the ending side and go around, and then in the middle we could put that curve in, because by that time we could figure out what the chord bearing is, and then we could enter in the curve. Right. So I was just wondering if you could do anything like that in Arc Pro, or do we really have to know what all the curves and tangents are, or what all the lines and curves are going to be to enter in and traverse?
Yeah, that's a great question, because that's one of the things that, and I'll kind of give you the answer, we've already lost on here. Because, and if you remember the discussion we started before we started the meeting regarding the way in which curves were actually stored inside of the ArcMap. Parcel fabric is a complex geometry, and it had a separate table inside the database to do that. Inside of ArcGIS, that's not the case. They've abandoned that complex geometry, so that really all we have now is we have a curve. That's it. So that if we go, so what would happen is that inside of ArcMap, let's get out of here. Let's just go to create here. Straight line. Inside of ArcMap, we could create a chord, right? And then go back and go to the attributes of that chord and say, well, you know, that's actually got a, and this, so here, this is 425 feet. And we could go back and say, well, this is really not a straight line. This is actually, because this straight line was part of something else. And we could say, well, this actually had a 250-foot radius on it, and that the arc length was maybe 490 or something on here, right? Can't do that here, because once it's stored as a straight line, this isn't part of something else. This is literally a line. So that you can see right now, I have got a straight line that I have got curve parameters on. This is not a curve anymore. When you draw it the first time, it's a simple feature. So you can't change curves into straight lines and straight lines into curves. That functionality is gone. The best that you could do is you could do point to point to point, and then go back in here and use endpoint. Say, here's a curve, and then you could right click and you can say it what the radius is on here, or you could actually go and input the curve that way, but it would not be replacing the line. All right, it would instead be a new feature that's being stored on there. So to answer your question, and that is a great question, we've lost that functionality by going away from that complex structure into simple features. We can't do that trick anymore. And for those of you that may not be familiar with it, it used to be that we could have a traverse, all right? And on that traverse, we could have, oh, there's a curve here, but it would define what the chord bearing is and maybe the chord distance or something. It'd be enough that we could define what these are, and we could input the chords and the bearings to build out the traverse so that we could eventually close it out. And then we could go back and say, well, this here, this line here, this is actually a 100-foot or 120-foot radius curve, and it would change that geometry into a curve. Can't do that anymore. That's gone. You could still, again, you could in the traverse, if you wind up not being able to figure out how to go and do that, you could put the chord in. It just means you're going to wind up deleting that when you replace it with a curve instead. My recommendation is, if you really are not sure what's happening here, you can go in here and let's put something in here. And then once you get to this point, once you're ready to put the curve in and you're not sure, then go and bring up this element. Bring up the circular curve constraint on there. And here you can play around with, okay, so what is the radius? What's the chord length on here? And you can go and input this here, 125 feet, and see where it's going to be before you actually input it. And then once I go and input it, you'll notice it stored all those in there for me. So unfortunately, we can't go in there and just automatically create the chords and then go back and use that trick to turn them into curves. But what we do have and what we can use is we can use this trick of inputting in lines and then going and creating a curve in the middle of it there and going from there. Andrea then goes and says she uses the curve calculator tool in ArcMap when I don't have all the components. Bummer that ArcGIS Pro doesn't have similar tool. Well, while it doesn't have exactly the same tool, it does have this curve. And this is literally the curve calculator. What it doesn't have is, it doesn't have them all listed where it tells you what these other things are. But instead, it's like, well, if you know this, and again, I can know the arc length, I can know the central angle here, maybe this is 90, it will then draw it out, but it won't tell me what all those other components are inside of here. It is set up for drawing, not necessarily for calculating all this. The other disappointment that I have is that in here, if I note my attributes of my line features, there's no COGA, or there's no central angle. There's no delta angle stored on here anymore. Nothing. It stores in this case, there was input a bearing here, and there was an input a radius and an arc length. It doesn't record the distance because this is not a complex feature anymore. The distance is no longer the distance field, which used to be the chord distance. That's not recorded anymore on a curve. The only thing that's recorded is the arc length and the orientation of it and the radius. Now, if I go and define a curve here as having a chord distance, all right, what's then stored? Let's make sure I've got this right one. I input it by using the distance field. Doesn't do it. the arc length. The arc length and the radius gets stored on a curve, and that's all that gets stored. All right. So the only thing we haven't done today is looked at and this is a, oh my gosh, Tori. I asked Tori to send me a spiral curve. I kind of can read it. Yeah, I'm going to pass on this, but I am going to cover real fast. If you know the parameters of a curve, you can go in here, and just as there is a circular curve, there is a spiral curve. And a spiral curve is a curve whose radius changes between the beginning radius and the ending radius. And these are traditionally along roads, along highways, super highways. Matter of fact, every one of us have driven on a spiral curve. When you have a cloverleaf intersection on a road, it starts out with the radius being very, very long. And then as you exit off of that highway, that radius gets sharper and sharper. It gets shorter and shorter and shorter to do a couple things, to slow you down and to go and have you turn faster and faster in. So that's where you use the spiral curve. There's spiral curves are used a lot in railroads, railroad rights of way, and some Department of Transportation use spiral curves a lot, even in the right of way descriptions on them. So there is a couple things. There is a direction, just like everything else, there's a direction on here. What is the starting radius and what is the ending radius? So in this case, let's say it's an infinity, and it's going to end at 300 feet. And the parameter that we're given is either a central angle or an arc length in here. Let's go and put 400 feet in here as the arc length. And you can see in here where it is actually changing the radiuses as it goes along. And you can densify this either by length or by the standard deviation as far as where it gets densified. The densification component is where is it going to put the vertices, because it can't really store a spiral. There is no geometry type for a spiral. Inside simple features, there's a straight line, there's a curved line, there's a Bezier curve, there's an ellipse, but there is no spiral. So this is the way they've done it. Again, what's the tangent? What's the starting radius? What's the ending radius? What's the overall arc length or delta angle on here? Let's just do arc length on here. So it's 400 foot long. Does it go to the left or the right? All right. And this final thing is, well, how do you want me to go and store the geometry? Where do you want me to put these vertices? Because it's going to be a straight line. It'll be an approximation of it. So let's just do it every 25 feet in here to put a vertex in there. And when I hit enter, it actually has stored in there the overall shape length, the actual angle or direction that was used. Here's the radius 1, which was the infinite. And then here's the radius 2, which is the radius I gave it at the end of it, 300 feet, and it's a radius to the left. And it is stored as just a straight line in here. So if I go in here and tell it to go and look at At the vertices, I can see that's how it did it, how it drew it. It drew it as a straight line and then inserted vertices by however I went and defined it to do the densification of the line. It's a nice first step of doing spirals and be able to allow us to go and put that in. And depend upon how dense you want to make that, you can input it. That, by the way, can get stored and used inside the parcel fabric also, because it's storing it as a densified line more than anything else. Kelly says, we have these kinds of plans. They are horrendous to read through and map out. They are. And I will completely agree with you on that. I wish there was an easier way to go and do that, but unfortunately, that's what most of these right-of-way highway maps look like. All right, we are approaching the 4:30 time limit. Are there any other questions or any discussions on here before then? We've gone over a lot of things in here. The important things I want you to come away with is the definitions of the components of a curve, the actual arc of the curve, and then the various elements of how they're stored, the radius lines, radius distance, the tangent lines, tangent distance, the chord length, and the chord bearing, tangent bearing, radial bearing, and then sort of the relationships between there. I can, again, if you start thinking of curves as being nothing more than triangles, they begin to make a whole lot of more sense. I can tell you that, and I'm going to tell you how old I am now. When I started surveying, we didn't have handheld calculators. We actually had a big Monroe calculating machine in which you had to punch in numbers and then pull an arm, and it would go and give you calculations from it. So that when we learned how to, when I learned how to do a curve, it was, listen, if you really want to get into this, all curves are triangles. So all you're doing is you're calculating the components of a triangle for that curve. So that when we used to have to go and figure out how to get, and let me go and erase this out. When we would figure out how to lay out a curve, we were always calculating what's the angle between here and this point, and then what's the angle between here and that point, and what's the angle between here and that point, and it was nothing more than triangles. Triangles everywhere. Everywhere is all a surveyor sees. All right? So hopefully you all learned something. Hopefully it helped you and will help you in putting all this information. We went over some of the things that work right now, some of the easier ways to build curves. What's the best way to input a curve in a subdivision? What's not the best way to do it, but sometimes you have to do that. And I thank you all for coming. We're going to stop the recording now and we'll move into. Thanks for attending, and we hope you enjoyed this workshop. If you have questions, would like some more details about anything we discussed during this workshop, or if you or anyone at your organization would like information about training, support, or ways in which we can help you with your GIS needs, please contact me at frank@pandaconsulting.com or call me at 561-691-3277, and we can discuss how we can help you with your needs.